Hello, Math 1224. This is Dr. P with Lesson Supplement 2-01 called How to Turn Your Thinking into Integrals. Now, just as a reminder, the lesson supplements are not extra credit assignments. They're not for coins. You're not in any way mandated to watch these. They're just meant to add a little bit of texture or flavor to what we talked about in class and possibly help you with some of the homework assignments. So with that said, let's just dive in. I received questions from a number of you about this problem number 2 from the activity that I had you do on day 1. It's the one about Dr. P's training run where he runs 20 miles, and at every distance you're given the speed that he was running at that distance. So this is not a speed versus time graph, this is a speed versus distance graph. And you're asked to figure out how long it took for me to run the entire 20 miles. All right? So first thing I want to do is talk about an approach that some of you used in thinking about this problem discretely. So everything that we do in calculus, the major intellectual oomph of what's going on is that we are progressing from discrete thinking to continuous thinking. That's really what calculus is all about. That's what makes calculus such a stellar intellectual advancement in the way that we do science, is that we're able to move from discrete ways of thinking, where we're thinking about, for example, sums that have a finite number of terms, to something that's continuous, like an integral. So I'm going to demonstrate how that works on this problem. So first let's erase that, okay, and I'm going to move this over a little bit, and I think I might even zoom out, because I'm really just going to use the graph here, but I want to be able to record some work over here on the right. Alright, so I'm looking at this 20-mile run, and the only way of thinking I have about this problem right now, let's find a color that works, there we go. The only way of thinking I have right now is that I know about certain distance intervals that I ran, like the interval from 4 to 6 miles, for example, and I know how fast I was running during each interval. So if I know how far I'm running, and I know how fast I'm running, I know that I can figure out how long it took me to run that interval, because I know from high school algebra that distance equals speed times time, which means if I'm interested in finding time, then I can solve that equation and get that time equals distance over speed. Alright, so the way I'm going to think about this problem is I'm going to divvy this integral up into a bunch of subintervals, and just to make just so that the focus here is on the idea rather than on the computation, I'm going to use a fairly small number of subintervals. I'm going to use just 5 of them. And for each subinterval, so let me mark off the subintervals first. There we go. Alright, so those intervals are going to be 0 to 4, 4 to 8, 8 to 12, 12 to 16, 16 to 20. And for each subinterval, I'm going to pick a speed that I'm going to use to represent the speed for that entire subinterval, even though we know, of course, that the speed is variable within each subinterval. Alright, so just marking what looks like sort of a nice middling speed in each interval. Actually, I'm using the midpoint because that seems to work well in each case here. Okay, now you'll notice I haven't drawn any rectangles yet. That's because the thing I'm going to calculate this time is not the area of a bunch of rectangles. It's actually a different calculation from that. Instead, I'm just going to look at each subinterval. For example, take this first one from 0 to 4. Okay, there we go. So over that subinterval, I run 4 miles. And I'm going to divide that by the representative speed I picked, which is about 6.3 miles per hour. Now you'll notice I wrote miles per hour as miles over hours because that reminds me that whatever this gives me is going to be some number of hours. And I'm actually not going to bother calculating it here. If you want, you can get out a calculator and do it, but I'd actually rather focus on the result of this calculation and what it looks like when the whole thing is done. So now I'm just going to keep going. Interval 2. Interval 2, I get 4 miles over, looks like about 6.5 miles per hour. And then, let's see, just going to zoom that out a bit. There we are. And then for interval 3, I get 4 miles over what looks like about 5.8 miles per hour. And then for interval 4, I'm going to get 4 miles over about 4.5 miles per hour. And then finally for interval 5, I get 4 miles over about 3.5 miles per hour. Remember, each of those represents the estimated time it took me to run some subinterval. That's delta t there. So I've got five amounts of time which are going to get added up to give me the total time it took to run 20 miles. Try saying that 5 times fast. All right. Anyway, so the total of these times is going to be the sum from I equals 1. Let's do that a little bit neater there. The sum from I equals 1 to 5 of delta x, that's the change in my distance run, over g of x sub I. Now remember, what is that g? That g was the name of this function that represents how fast I'm moving after x miles run. So remember, each of these things here, each of these terms of this sum represents a distance over a speed. So this entire thing represents some amount of time. And then what this sum is doing is it's taking a total of 5 terms. The first term is this quantity here, the second term is this quantity here, and so on. All right, so that is a discrete way of thinking about this problem. And that there's nothing wrong with thinking about it discretely, except that it doesn't produce an exact answer. Now, really, nothing I'm going to do here is going to produce an exact answer because I'm working with a graph that isn't defined by any particular exactly defined function. But I do want to demonstrate how we can turn this way of thinking into an integral. That's the whole point of the video. So what if I take this graph here, and instead of chopping this interval here up into 5 subintervals, I chop it up into an increasing number of intervals and let the number of intervals go to infinity. Then what I'm doing is I'm changing this sum here so that this delta x gets very small. The number of terms grows without bound. And when you do that, anytime that you do that in calculus, what you're doing is you're turning a sum into an integral. So the limit, as the number of subintervals goes to infinity, is going to be, oh, by the way, one thing I just realized is that this equal sign here shouldn't be an equal sign. It should be an approximately equals because everything that we did there is an estimate. The actual total time, you'll have to forgive my handwriting, I'm still not quite used to this. The actual total time is going to be equal to the integral from x equals 0 to x equals 20. Remember, those represent distances run, so I'm running from 0 miles to 20 miles, of dx over g of x. Now, what does that represent? So that means I'm going to let x, the distance run, go from 0 to 20, and at every point, I'm going to consider a very tiny change in my distance, so that's a small distance run, divided by the speed at which I ran that tiny distance. That's going to give me a tiny change in time, and then adding up all of those bits of time, all of those continuously small bits of time, gives me the total time it took me to run the 20 miles. So that's how I turn this way of thinking, this idea of adding up a bunch of bits of time, into an integral which adds up infinitesimally small bits of time. And that's the idea of that problem. And I'm going to give you some questions this week where your job is to do something similar. Think about how you might think about the problem discretely at first, that is, think about it in terms of finite sums, and then think about it continuously. That is, let those chunks of time, or chunks of whatever, go to 0, and see what integral results. All right, that's the end of this video. Please let me know if you have any questions.